Linear algebra is very useful for quantum mechanics. We've already used a lot of the notation and terminology of linear algebra when we say, for instance, that two wave functions are orthogonal to each other. But quantum mechanics puts its own spin on things. In part, for instance, because we're not dealing with, say, three-dimensional Cartesian coordinates. We're dealing with a complex vector space that describes the state of a physical system. So dealing with complex numbers and dealing with vector spaces in a more general way is very useful, especially as we move away from simply solving the Schrödinger equation, but to manipulating solutions to the Schrödinger equation to infer the properties of physical systems. So linear algebra will be useful in the coming chapters. To justify why this is useful, I'm going to make a couple of analogies. There are some things that we can say on the basis of vectors. We have vectors, A. We can make dot products between two vectors. We can express a vector A in, say, Cartesian coordinates, ax x hat plus ay y hat plus az z hat. We can also express some vector A in a different coordinate system. I'll call it a sub alpha, not x hat, excuse me, alpha hat plus a beta hat plus a gamma hat, where now the hatted vectors here are unit vectors, and the numbers ax, ay, az, a alpha, a beta, and a gamma are simply components. They're simply numbers. If these x, y, and z, alpha, beta, and gamma represent different coordinate systems, we can still say that this is the same geometrical object, A. The vector A is not changed by expressing it in different coordinate systems. It exists independent of any coordinate system. And of course, we can also take dot products of unit vectors with themselves and get 1. Quantum mechanically speaking, each of these expressions in terms of vectors has an analog. The vector A, that's what we've been talking about so far as, say, psi of x. That's the state of the physical system, the wave function. Taking the dot product of two vectors, that's our integral from minus infinity of, say, psi sub a star of x times psi sub b star of x integral dx. Expressing a vector in terms of one coordinate system versus in terms of another coordinate system is essentially the difference between looking at the state of the system as the wave function psi of x versus the wave function in momentum space, the wave function phi of k, which we got by taking Fourier transforms back when we considered the free particle. Finally, taking the dot product of a unit vector with itself is like saying the integral from minus infinity to infinity, back with our expression of the dot product, of psi star psi dx is equal to 1. That's our normalization condition. Essentially, the analogy between vector operations and the wave function, given these particular definitions of something like the dot product, is a good analogy, and in fact, it's a mathematical identity. You can think of, for instance, the dot product as adding up similar components, like the x component of A multiplied by the x component of B plus the product of the y components and the product of the z components. Looking at it in terms of the wave function, here we're taking the component of the wave function at some position x, multiplying it by the component of some other wave function at the same position, repeating that over all different positions, and adding up all of those different effective components, position components of the wave function. So there are analogies between linear algebra and quantum mechanics, and they actually end up being very useful. Quantum mechanics, as I mentioned, puts its own spin on things, and just for the sake of being able to use the actual notation that people who study quantum mechanics use, instead of writing a vector A with an arrow on top of it, we write it like this, with a line on the left and an angle bracket on the right. This helps us to distinguish what's a vector from what's a scalar. It also helps to distinguish us from what's been complex conjugated to what's not been complex conjugated. And just staring at this slide, this should not be psi b star, this should just be psi b. Apologies for the error. Keeping track of what's complex conjugated is obviously rather difficult because I've just made a mistake doing it. But keeping track of what's complex conjugated, we do with this notation by writing complex conjugated vectors essentially the opposite direction. Now, Being somewhat punny, the physicists that invented this notation decided to call it bracket notation. And being physicists, they decided that this would be called bra, and this would be called ket. So if you see something like this written, you should read it as either the vector A or ket A, whereas this would be read as bra A, or the vector A complex conjugated. You can think of these in terms of the wave function as this representing psi and this representing psi star, and we'll come back to what that notation means in the context of inner products in a few slides. But for now, this is the notation that I'm going to be using to represent vectors in quantum mechanics, where now the vector is a more general thing than just something in, say, three-dimensional Cartesian coordinates. We're talking about something even more general than the wave function. It represents the state of a physical system independent of any coordinate system. So it's not psi of x. It's the state of the system, which can be represented either by psi of x or phi of k, or an infinite sum of stationary states to the solutions, stationary state solutions to the Schrödinger equation. They're all different representations of the same physical state, and that physical state is what we mean by writing something like ket A. So that's the overall analogy, and that's the notation. Just to very briefly review some of the basic properties of vectors. We have vector addition. We can say vector alpha plus vector beta is equal to some vector gamma, which of course is also equal to the vector beta plus the vector alpha. Addition is commutative, and addition of two vectors gives you another vector. We of course have a zero vector. If we take some vector alpha and we add the zero vector to it, we just get alpha back. We have scalar multiplication. I can write something like A times the vector alpha and get something which I'll call the vector gamma temporarily, where gamma is just some vector that essentially points in the same direction as A but is only slightly longer or shorter, having been scaled by A, hence the term scalar. This scalar multiplication is distributive. I can write some scalar A times vector alpha plus vector beta as alpha times vector A, sorry, getting my notation mixed up, A times vector alpha plus A times vector beta. Or alternatively, I can look at A plus B times some vector alpha as A times the vector alpha plus B times the vector alpha. So scalar multiplication distributes across addition versus of vectors and across addition of scalars. Scalar multiplication is also associative, of course. I can look at A, B times the vector alpha as either A times, pardon my notation, as either A times B vector alpha, or B times A vector alpha, or as AB vector alpha. These are all equivalent. Scalar multiplication commutes and is associative. I already mentioned the additive identity here. There's a multiplicative identity as well. I can multiply a vector alpha by the scalar 1 and just get the vector alpha back. But those are our basic properties. Hopefully this is familiar. Either you can understand it from studies of linear algebra in general, or just by analogy with the day-to-day use of vectors in physics. Moving beyond the basic structure, one nice feature of vectors in linear algebra is that we can make linear combinations of them. For instance, if I have some vector A alpha plus scalar B vector beta plus scalar C vector gamma plus etc., I have a combination of vectors, each multiplied by scalars and all added together. This brings to mind a couple of useful concepts. First of all, linear independence. If I can write alpha is equal to, say, A times some vector beta plus C times some vector gamma, then you say this set, alpha, beta, and gamma, is not linearly independent. If, however, I cannot write alpha as a sum of beta and gamma multiplied by appropriate scalars. If there is no choice of alpha and A and C, such that I can make a sum of beta and gamma that equals alpha, then we have a linearly independent set. Alpha, beta, and gamma would be considered linearly independent, or alpha would be considered linearly independent of beta and gamma if it cannot be made by a linear combination of beta and gamma. If you have a bunch of vectors with which you can use to construct other vectors, you'll never get anything that's linearly independent from those vectors, but you can get vectors that are not in your original set. For instance, suppose I have some set of vectors, xi. If I can write, let's say, my vector alpha as a sum ci xi, where I goes over the range of all of my vectors in this set, I've expressed alpha in terms of xi. In this case, I would say I have expressed alpha in the basis of states, or a basis of vectors given by xi. This ci here is, in some sense, c sub I is the x sub I component of the vector alpha. So if I have a set like this that I can use to express other vectors, you can describe that set as being a basis. Bases have other properties, and you can construct bases that have additional properties than this. Some bases are better than others, especially if you have a variety of purposes you want to accomplish. But the notion of a basis is that it is a set of vectors that can be used to construct other vectors. And the set of vectors that can be constructed from a basis, the space of vectors that can be constructed from a basis, is the space spanned by the basis. So, for instance, let me write, if every alpha in some space, the space that we're interested in, can be written like this, alpha equals sum over I c sub I times ket x sub I, we say the set of basis vectors x sub I spans the space we're interested in. For instance, the x, y, and z unit vectors in Cartesian three-dimensional coordinates spans all of three-dimensional space, three-dimensional Cartesian space. So if I have a set of basis vectors that spans a space, the dimension of the space is the minimum size of a basis. So if I have, say, in 2 dimensions, in the plane of this sheet of paper, if I have a vector that points in that direction, and a vector that points in that direction, and a vector that points in that direction, all in the plane of the screen here, I have 3 vectors, but they are not linearly independent, since I could construct this vector from a combination of these 2 vectors, or in any other order. Any of these vectors can be constructed by a superposition, by a linear combination of the other 2. And I have 3 vectors, so you would think I have a 3-dimensional space, but it's not the minimum size of the basis. I could say, drop this vector, just work with these 2, and still have a set of vectors that I could use to express any vector that lies in the plane of the monitor. So that's a little bit about superposition and linear combinations and some of the terminology that we'll use to describe what happens with them. The next major topic is inner products. The inner product in quantum mechanics, the inner product between 2 vectors is written like this. I'll keep using my Greek letters. Bra alpha ket beta. And you can think of this a little bit like A dot B, working with conventional vectors, but it's different. And it's different in a couple of ways. First of all, we're working with complex conjugates now. So if I wrote alpha beta, inner product, and I compared that with beta alpha, I would have to take the complex conjugate. If I exchange the order of the two vectors in an inner product in this complex number space, you have to take the complex conjugate of the result. We do have some familiar results, though. For instance, if I take alpha and dot it with itself, take the inner product of the vector alpha with the vector alpha, you get a real number, and it's going to be greater than or equal to 0. You also know, and this should hopefully not surprise you, that if alpha dotted with itself, the inner product of alpha with itself, equals 0, if and only if alpha is equal to the 0 vector. It's very common to write the 0 vector as just 0. It's usually reasonably clear from the context whether you're talking about a 0 vector or a 0 scalar. This is a little bit like writing 0 without units. We do that a lot in physics. We'll say, how tall, how long is this? Well, 0. You wouldn't say 0 meters or 0 nanometers or 0 kilometers because it doesn't matter what the unit is if it's 0. It doesn't really matter if we have vector 0 or scalar 0, it's still 0. We also have some familiar concepts. For instance, if I write alpha inner product with beta, and that equals 0, we say these two vectors, or states, are orthogonal. If we have a set of states, xi, such that xi dotted with, or inner product with, xj is equal to the Kronecker delta ij, we say we have an orthonormal set. This xi set is orthonormal. For instance, if I write x, y, z as unit vectors, they form an orthonormal basis for three-dimensional Cartesian coordinates. Now, note that in all of this, you might think, well, I'm taking the inner product between two vectors. I know how to do that. I figure out what the x components and the y components and the z components are, I multiply them together, and I sum them up. But I want you to start divorcing in your mind the notion of something that looks like this from something that looks like this. Because we don't necessarily have components that we want to consider. We have physical states. And it turns out the mathematics of linear algebra can tell us about the properties of these states and how they interact without actually expressing them in any basis. Of course, we can do a lot of things when we do express them in a basis as well, but the vectors themselves can live without the basis. Having defined an inner product, it's also useful to define a norm, and this is occasionally written as, like, if I write two lines with an alpha in the middle of it. This is more or less defined to be alpha dot product with itself square rooted. Since the square root, or since the inner product of alpha with itself was defined to be a real number, positive real number, the square root of this is also a positive real number. This is our unit of, or our definition of length, if you want to think about it that way. And if we have some vector alpha with norm 1, we say it's normalized. It's a unit vector. A normalized state. Your normalized state is a slightly more useful term than saying it's a unit state. You don't hear unit state, though you would hear unit vector. You will also hear normalized vector. So normalized is sort of a more general term. Finally, now while I have said that vectors can live without the components, it is useful to express things in terms of components many times. So if I have a basis of unit vectors, an orthonormal basis set that spans the space that I'm interested in this case, three-dimensional space, I can write the vector alpha as alpha x times, keep wanting to write x hat, times the vector x plus, alpha y times the vector y plus alpha z times the vector z. Likewise, for some vector beta is beta x vector x plus beta y vector y plus beta z vector z. And I can write out things like the inner product alpha beta, and it looks pretty much the way you would expect. It looks like alpha x star beta x plus alpha y star beta y plus alpha z star beta z. You can also, of course, write the inner product of alpha with itself and get alpha x star alpha x plus alpha y star alpha y plus alpha z star alpha z, which you recognize as the squared magnitude of all of those components, all summed up together. Each of these components, incidentally, these alpha x, alpha y, alpha z, beta x, beta y, and beta z, can be found by taking inner products. Alpha x is defined more or less as x inner product with alpha. Likewise for alpha y, being defined as y, unit vector, unit bra, y, inner product with ket, alpha. And likewise for z. This is all in three-dimensional space, and we can actually work in higher dimensional spaces as well. Nothing here is really limited to 3 dimensions. If I have some set of orthonormal basis kets, x sub I can write the vector alpha as the sum over I of some alpha sub I times x sub I, given suitable definitions for alpha sub I. In particular, alpha sub I is x sub I inner product with the vector alpha. And you can write out expressions for alpha inner product with beta. That's a sum over I of alpha sub I star beta sub I, or the inner product of alpha sub I with itself. Not alpha sub I. The inner product of vector alpha with itself is the sum over I of alpha sub I star alpha sub I. Total sum of all of the squared moduluses, whatever, of all of the components of alpha expressed in this basis. So that's a little bit about how linear algebra is expressed and some of the things that we can do with it. As an example, I would like to check your understanding with the Schwarz inequality. This is just an exercise in manipulating vectors, but the Schwarz inequality, and this is something that can be useful in quantum mechanics, what it states is that the inner product of some vector A with some vector B, squared magnitude, is always going to be less than or equal to the squared magnitude of A multiplied by the squared magnitude of B. So, inner product of A and B, squared magnitude, is always less than the inner product of A with itself and the inner product of B with itself. This is the squared norm of A and the squared norm of B. So your task is to check that this inequality holds for the 2 vectors given, where here x, y, and z is an orthonormal set that spans some 3-dimensional space of interest. Note that I'm not necessarily talking about 3-dimensional Cartesian space here, but it's a good analogy to keep in the back of your mind if you're having trouble imagining what these things should look like.